Thank you. You guys hear me? Good. As you said, my name is John McIntosh. I'm here to talk to you today about a tool I wrote called ghidriff, or Ghidra Binary Diffing Engine. I've been working on this for the past year, and I'm releasing this open source. And it's kind of a summary, or it contains all my lessons learned, probably for the past 3 years of me doing patch diffing. A little bit more about who I am. On social media, I'm Clear Blue Jar. I'm currently a security researcher at ClearSec Labs. I've got about 10 years of experience in the security industry, open source dev, and 3 years ago I wrote something called CVE North Stars. And it was really just a tutorial on how to do patch diffing leveraging Ghidra. And it was really, I wrote it for myself and I published it because it seemed pretty useful to teach others. But really the idea behind that, CVE North Stars, was to leverage CVEs as a way to kickstart your vulnerability research. You can start with a CVE and understand what the root cause was and leverage patch diffing to do that. And then you get a head start in your vulnerability research. Yeah, I've got to go this here. The main motive of this talk is to encourage you to do pip install ghidriff. Now that's Python, and if you're Python adverse, or if you're Ghidra adverse, which needs Java, I have a Docker container for you, so you have no excuse to not try it at least. Explaining the name, ghidriff is Ghidra and binary diffing combined. I have another tool called GhidraComp, which is a command line decompilation tool using Ghidra. Hopefully this name works for everyone. Now, as I say all these words, I say binary diffing. You might have some questions of what these things are if you're not familiar. Ghidra, you're probably pretty familiar with if you're in this field. Python, why did I use Python to speak to Ghidra, which is written in Java? And then why do I have yet another diffing tool? Like, isn't this a solved problem? Don't we have bin diff? And the answer is yes, but I'm going to explain as to why I've created a new tool. And in summary, this is our schedule for today. I'm going to teach you, we'll put everyone on the same page as to what binary diffing is. I'll give you the background and motivation. We'll look at some of the internals for the tool, some of its features, and we'll look at some real-world CVE diffing to see how this is useful. So let's start. Let's go with binary diffing. Let's look close. What is it? Academia calls it binary code similarity. We know it as bin diffing or patch diffing. If you Google for patch diffing right now, I think my website has some good SEO because I'm the #1 hit, and it's just telling you that patch diffing is a specific form of binary diffing, of comparing two binaries to see what is similar and what is different. And the patch diffing is doing that binary diffing but related to a security patch, looking at a patch binary and its vulnerable version and seeing what the differences are. This is more of a visual of that. The basic idea is to line up, to match all the functions that are available to you. The ones that are the same, we don't really care too much about. The ones that are different, those are more interesting. Or maybe there's some new functionality that has been added, or some that has been deleted. That becomes interesting as you look into the binary itself. You're trying to filter out everything that's the same, look at the differences, and so just to see what could be interesting. Why do we do it? The general use cases for binary diffing would be, say you're a reverse engineer and you're 80% done with your reverse engineering work and a new version of the binary comes out, you're like, no, I was just done. You can use binary diffing to kind of match those functions back, port over your changes and your reverse engineering work to the new binary. And vulnerability research is typically used so that you can go and look at actually what the root cause is. You can determine, like leveraging patch diffing, you can say, oh, did they actually fix the bug or was it more of a shallow fix? And for malware analysis, you can do binary diffing to find malware lineage, to trace things and say, oh, this malware is descended from this version. So those are kind of general use cases. If you look at Halvar Flake here, he posted, he's one of the godfathers of patch diffing. He wrote, he's one of the authors of bin diff. He said, it's almost as if a variant analysis in patch diffing is useful. And what he's doing is he's quoting Google's report that half of the 0 days that came out in 2022 were just variants of previously known bugs. And so he's just reiterating the fact that patch diffing is used today by attackers, by researchers, and it's a good way to kind of find new bugs and variants. So how do we do it? How do we do patch diffing generally? You can ask Bing, and Bing will say, oh, you just take the source file of the original binary and the source file of the second binary, and you run diff on it. Well, that doesn't really work and that works well for text, but we're not dealing with text. We have, here's a hex dump of a Windows PE file, and you have your MZ or MZ, and if you compare those two together, it's not going to make much sense. But luckily, we live in the day and age of software reverse engineering frameworks, and we can kind of handle these problems. We can look at you can take the text itself and make distinctions from it. And SRE tooling, they take these complex binaries and they distill it into objects, right, and relationships that we can compare. You'll take the hex that we see, and we can look at the listing for it, or you can look at the decompiled pseudocode view. You can see all the call graphs and relationships and how they exist, and they start to make sense of these binaries. And basically, what I'm trying to say is all of these diffing tools rely heavily on these platforms. The purpose of diffing tools is, I've said before, just to find what's been added, what's been deleted, and what's been modified. And is this a hard problem? I'm saying it is. It's a solved problem. We have many tools to do this, but it continues to be difficult because of all the relationships that exist within a binary. However, from his 2004 paper, this is early days of bindiff, it says it takes relatively little work to change the source code and recompile, but while the analysis of the object code will have to be completely redone. Well, he's just trying to say that a small source code change can really affect how the binary looks after it's compiled. Now, there might be compiler optimizations that change it for the next compilation, or the compiler, maybe the wind's blowing a certain way, and the next time you compile it, it's a little bit different. He's just saying generally it's not a fair problem. And so every diffing tool is trying to bring symmetry back to the asymmetric problem of reverse engineering binaries. So what do we have today kind of for our options? Quick history, and here again, the godfathers of patch diffing, Halvar, Flake, I believe, and Rolf Rolls was the original authors of bindiff. This is a slide from Black Hat 2004. So here we are, almost 20 years later, talking about patch diffing still. But he was talking about patch diffing back in 2004. So bindiff has been around for quite some time. It has become, it's become a verb, as Halvar had said. And here's a quick look at what it looks like. Once you analyze a binary, you can export all the functions and data from the analysis into bindiff, and bindiff will go through and match each function. I'll put it into a big table. I don't expect you to read that, but it does the matching for you. It gives you a nice control flow graph view diff, kind of a side-by-side. You can tell what things are the same, what are different. You can zoom into the basic block itself, and you can tell the difference. I do find it hard to read assembly, and I think the only flaw I've found with bindiff is it doesn't have the pseudocode side-by-side diff view. This is a slide from Maddie Stone's presentation back in 2019. She kind of did a big review of all the patch diffing tools at the time. It was about a similar time frame when I was studying patch diffing for the first time myself. But she used bindiff to solve her problem of reverse engineering a WhatsApp bug, and she gave bindiff the best review. There's another option out there right now called Diaphora. From its README, it's at version 3.0 now. It's been around since 2015. It works with IDA. It's a plugin for IDA, and it gives you that side-by-side diff view that's missing from bindiff, and it kind of gives you a table view match. So I think it's well integrated. I've not used it. I have friends that have. They say it's pretty good. It didn't work for Maddie Stone in 2019 in her review here. But I think since then it's been much improved if you look at their release, and I think it's pretty popular. We'll talk a little bit about version tracking tool. I have the most experience doing patch diffing with the version tracking tool. Now this is built into Ghidra. It looks like this. At the top you'll find all the matches it's done for the functions. In the middle, kind of what's been missing or added, and at the bottom it does have a comparison for the assembly, but not a side-by-side code diff view. When you start it up, the version tracker itself, you see this screen, and it kicks off two code browsers as well. And these code browsers show you both the source function and destination function, and allows you to navigate through after you found your matches. Here's a picture of the two code browsers, kind of side by side. And overall, I feel like the version tracking tool is the Millennium Falcon of patch diffing tools, and not because it's fast, but because it breaks down a little bit, and you have to kick the side, and then it starts back up again, and it works for you. And in the end, it's worked really well for me in my research, and you can get there. But I have found some issues with it, and that's probably why I'm standing before you today with a new tool. Maddie Stone, again, back in 2019 for her big patch diff review, she didn't include Ghidra in the mix, but here's my take on this, my same review of the version tracking tool. It does have some good matching algorithms. It's missing some of the structural function correlators or matching heuristics that are common both in bindiff and diaphora. It doesn't have that pseudocode diff view, and some of its scoring is confusing. And I mentioned before, it's not fast. It's slower than the other two. Okay, so those are kind of the top three. But kind of how do they work under the hood? Every diffing tool is only as good as the underlying SRE tool framework it's using. So it relies heavily on Ghidra or IDA or Binary Ninja, whichever one you're using. Bindiff relies on IDA, Ghidra, or Binary Ninja. Diaphora is tied to IDA. Version tracking to Ghidra, and my new tool ghidriff is obviously riding on top of Ghidra. For function matching, in the end, binary diffing is really just a game of matching functions. You're trying to find you want to match all the functions, all the added, deleted, and modified ones, so you can start to make sense of the differences. Typically, you're starting out with a function matching that's very specific and very exact, like exact byte for byte. And then as things move on, you progress towards things that are more speculative. And each diffing tool, they have different names. Bindiff calls it matching algorithms. Diaphora calls function matching heuristics, and Ghidra went with correlators. And they've all posted their list of the matching that they do. You can go on the website and kind of see more of the details of that. But in general, there's three high-level matching methods that you're using to take every function between two binaries and to tell if they're the same. Now, the most exact is the syntax version, where you're comparing byte for byte. You can compare them semantically to say, do these functions mean the same thing? I think that's a harder problem. I have talked to some guys actually here during the conference that are looking at that very issue. I think it boils down to like the halting problem. But most of the ones I have seen have been syntax and structure. And structure kind of came out of Halvar's paper from 2004, looking more at the control flow graphs to tell if two functions are the same. A quick example, you're not going to be able to see this code, but all this is showing you is a function that's taking every byte and then hashing it. And so that's more of a syntax style. A structural matching would look more at the edges and nodes of a graph. So like say you take a single function and you can run an algorithm on it to like count the nodes, count the edges, and do a little bit more than that to compare the two functions. But all the tools are looking to provide that complete list of matches so that you can classify the functions. Once you know all the functions have been matched, you can say, oh, I can match this function from my old binary, so it's been deleted. Or I can match this function from my new binary, so that's a new function. And once you have this full classification, you can say, oh, you can make decisions, oh, this is a matched function but different, or kind of classify them well. And once you can classify them well, you can actually start to see what's important. This is a quick diff showing you the deleted, added, modified. If you just look at the added functions for this patch, if this is a Windows binary, for a recent CVE, there's three functions that have been added to this binary. That's a convert full path to long UNC, is valid file path, safe delete file by handle. So just looking at the functions that were added to a vulnerable binary and a patch binary, you just say, oh, they probably had an issue with an arbitrary delete somewhere with this. You could go, and then once you go and diff that function that had been changed, you can see them deleting the unsafe API and adding the safer API. And you're doing this all by just looking at the changes between the two functions. One of the main points for patch diffing is that patch diffing, although it does highlight everything for you, it's not going to tell you exactly which functions were the vulnerable ones. You're going to have to do some reverse engineering work for that. But it helps you focus right down to what things matter. So it takes 1,000 functions and brings it down to 10 functions that you have to review. And it becomes really a powerful tool. So I was getting us all on the same page, hopefully, on what binary diffing is, kind of why it's useful, what it's used for. And now I'll talk about kind of like the background and motivation for building a new tool, or yet another diffing tool. Again, this came from my work back in 2020 when I dove into patch diffing and I wrote this tutorial. And I kind of had a workflow. I was reviewing several spooler CVEs from around the 2020 timeframe. And I was just seeing, like leveraging patch diffing, I could see over and over again, they were shallow fixing several Windows print spooler bugs. And I did some analysis. I'm like, oh, every time they missed the root cause until they finally fixed it and the bugs stopped coming for that path. And so what I concluded about patch diffing were three things. And yes, I'm quoting myself here, but with patch diffing, I feel you have a single source of truth. You don't have to rely on someone else's blog post. You don't have to rely on a GitHub POC. You can go and see for yourself what the changes were to the binary, or binary truth, I've heard it also called. You can seek binary truth with patch diffing. You can also, it teaches you about vulnerabilities. If you want to go learn about some integer overflow or some use after free, you can seek out those CVEs, do patch diffing on that specific CVE, and then go learn more detail about what that actually looks like in real software. And lastly, it's just fun practice. Like tonight, when you're bored and you want to go home, like, what am I going to do? I can patch diff something and learn something new, and kind of build up your RE skills along the way. And that's my Wednesday night typically for me, not Friday. But patch diffing became this permanent tool in my RE, like my reverse engineering tool belt. I wanted to dive into vulnerability research, and patch diffing was my way to get there quickly. I started doing quite a few patch diffs, and I'm doing this long workflow. I'm like loading up binaries, starting new projects, going through the GUI, clicking through links. And again, it became very repetitive. And then what do we do? What do programmers do when we find a repetitive, tedious task? Well, we write a script, right? And then from the script, ghidriff was born, rising out of the ashes. And I did. I wrote a script about a year ago. And the first script was a simple, one Python script, and all it did was really compare string symbol names. So leveraging Windows, you typically have symbols, and you can just look at the names and compare the functions that way. I originally called the Ghidra simple diff engine. I had some design goals of doing patch diffing and having some results. It's evolved since then, and I'm going to talk about how that's evolved right now. But ghidriff was born kind of out of necessity for me, doing one too many manual patch diffs and curiosity, wanting to know how it worked. The necessity portion was really overcoming the pain points, trying to reduce the number of steps needed in my workflow. I really needed that side-by-side pseudocode diff, and I was leveraging Ghidra to do it. They didn't have it. And it was difficult to share the results, to pull things out. And what am I talking about, the workflow? Typically for a standard like patch diffing workflows, you have to download your two binaries, create a new project, import those two binaries, analyze them, then run your diffing heuristics, export the analysis, or if you have bin diff, you can bring it into a new tool. There's just one too many steps there kind of going along. And after about 10 of those, you want to do something else. You want a command line tool. All you need to do really is download two binaries, run the command line, and then sit back and wait. Now, you don't have to wait too long. It depends on the size of the binary. The kernel takes a little bit longer. But then analyze the diff. And so I'll show you how ghidriff kind of solves that. For the decompilation diffs, or the pseudocode diffs, I was basically copy-pasting the pseudocode from each of the code browsers, both the source and destination. I was pasting that into VS Code and then doing the side-by-side. And it did work, but it's pretty painful to kind of manually do that each time. For reporting results, most tools, I think BinDiff has an image export. I'm not sure all the capabilities of Diaphora, and then Ghidra does no really exporting your results. It's all kind of interactive in the tool. I needed a way to get the results out and put them into reports that I was writing, or just easily say, oh, here's the diff, and show someone else, and it didn't have that ability. Now, for my other open source tools, I've done a lot of things with Markdown. I wrote this is from my blog post, talking about how mostly I try to make everything Markdown because it's so ubiquitous. You can find it on GitHub or GitLab, or every major blogging platform supports Markdown. So if you can output things in Markdown, they can be displayed pretty well, and they look pretty good. This is an example of, this is a Mermaid.js, which is also supported by many of the Markdown, like GitHub or GitLab or blogging platforms. Mermaid.js allows you to write in text a graph, and so I can take this text right here, and I can output a Gantt chart that shows the progression of CVEs and patches that over time. Now, I generated this with another tool I called CVE Markdown Charts that was a forerunner to both of these tools, but from that tool I learned how to leverage Markdown well, and I've implemented that now into ghidriff. Those are my pain points. Curiosity, Everyone needs a quote like this: "Curiosity is the wick and the candle of learning," or whatever needs to prove to myself that, or drive myself for learning. But being curious about something and actually doing it is what teaches you what's important, or actually helps you learn what you're trying to learn. When I wrote the tool, I was able to mitigate the pain points. I understood the complexity of patch diffing, appreciated it more, and then you also start to see what's important and what's not so important, as far as results for patch diffing and what to display, and then really helped me aid my vulnerability research with this tool. As well as Ghidra scripting knowledge went way up because I'm now building a tool with several features, and it just drives you. Doing something drives you to learn much better. I think you guys all know this. Okay, all right, we've got my motivation, my background. I want to build a new tool. I want to overcome my pain points. But what are some of the internals? It's kind of hard to see, but the basic is the input is 2 binaries, and the output is all of the Ghidra files after analysis. So it creates a new project for you and dumps out all that into a directory. And then your other outputs are your markdown report, a JSON file to capture all the diff results, and optionally an HTML if you want to display things that way. My design goals are to do patch diffing, do it simple, fast, and accurate, have it be resilient, the typical software engineering goals. I wanted the easy sharing of results, and I have this bullet called social diffing. It's kind of like social coding for GitHub. And all I mean by that is I want it to be easy to share results, post those on different platforms. And I've solved that with Markdown. So design choices. I went with Ghidra. They have really good support. I started scripting with them about 3 years ago, and they have really, when you submit an issue, they're really responsive. They have a strong community. I've got people outside of the Ghidra devs teaching me how to do things. I submit a new issue, they're like, oh, that's because that's not how it works, and they teach me along the way. So I've had really good feedback and support from them. And then they're constantly releasing new versions with new improvements. And then they have a rich programming API, and you have to deal with Java, and we'll talk about that here now. But one of the design goals is being simple, and the code, I went with Python. It's pretty straightforward. It's a simple Python package I have here. I have a test folder for PyTest. There's only about 6 or 7 files with any code in there in the first place, and it's pretty straightforward. You'll be able to see that when you review the code. Its main function is straightforward. It's saying we're going to parse our arguments, we're going to set up a Ghidra project, analyze the binaries and diff the binaries, and output the markdown. And that's, I don't know if that's 50 lines of code in the main, but it's pretty straightforward. Now, orchestrating Ghidra, how do I talk to Ghidra from Python? I did some research into this, and I put a blog post out called Ghidra Python Paleontology. I basically did a systematic review of all the available Python to Ghidra scripting plugins, and it's pretty extensive research I did there, and the best one I found was a project called Hydra. And this allows me to use Python 3 with Ghidra. Ghidra supports Python via something called Jython. Jython is a Python implementation written in Java. Now, it limits you to Python 2.7, and I've had a lot of issues with it, but this project kind of overcame that for me. Leveraging Hydra, I was able to just write Python 3 code and interact with Java directly, and also dynamically debug everything right in VS Code. So it became like a normal development environment. I leveraged Ghidra more as an API or a library. And so everything's written in Python, and I accessed Ghidra via Python through the library. But you wonder, maybe, is speed affected by that? And speed is not too much affected. I've done hundreds of patch diffs, several times with the kernel. And the reason why is because of this Python package called jpipe. And jpipe actually speaks directly to Java's JNI from CPython, and there's not really any lag there. You're trying to do as much as you can in Python, but if you have not checked out jpipe, and if you have a Java project, if you want to call Java code from Python, this is the project to do it. This is a quick, top or htop of me running my tool. So what I'm trying to show you here is it's leveraging all 8 cores to do the analysis, to do everything. It's not inhibited by Python's global interpreter lock or anything like that, and it remains fast. So I want it to be, the tool I want to be extendable. I wanted others to be able to add new diffing capabilities to it easily. And so I wrote this base class called the Ghidra diff engine. And according to Stack Overflow, an engine is a self-controlled, externally controllable piece of code. It encapsulates powerful logic. The diff engine itself handles all of the initial kind of workflow steps that you need for any kind of scripting project with Ghidra. It creates the project itself, it imports the binary, and it analyzes the binary. And all you need to do to implement a new differ with ghidriff is create a function, or fill in the abstract method of a function called find matches. And at the point of find matches, you're passed a pointer to both the old, you're passed a pointer to the old binary and the new binary, and those objects are Ghidra program objects, and you have full access to all the functions, all the data, and kind of you go from there to do all the matching. So you can build your own matcher just by implementing this find matches functions, and all you need to return is the list of unmatched and matched functions. Now, I say all, and that's a complicated process, and I've kind of had an evolution of those things. I started with something called simple diff, as I said before. It just compared the strings. I read Halvar's paper from 2004, and I'm like, oh, there's some structural correlators I should be adding to this, and that was my second instance. And my most recent version is called version tracking diff, which implements all the ones from Ghidra and a few more that are missing from Ghidra. I don't expect anyone to be reading any of this, but this is like the function signature for find matches. It's hard to see, but for my simple diff, I was just doing a name match comparison, like name and length, or maybe the address and the length are the same. Very naive, full of false positive function matching. For the structural matching, I started to look at the nodes and edges of all these graphs, and it kind of evolved from there until I finally got to this big list of function correlators, starting with the more exact ones, looking at the bytes, and then getting towards more of the speculative ones, like looking at strings and things. And I don't need to explain all of these, but this is the big list I have so far, and it works pretty well. So it works pretty well for us. I wanted to show you this, a correlator. Here is and maybe someone might cringe about this, but this is a class written in Python, but it's instantiated as a Java class, and that code is called from Java. It's a little bit like Inception-y, but this gives you an example of me accessing the Ghidra API from Python and how kind of straightforward that is. But there's a little bit of a learning curve for leveraging JPipe. This is just showing you the basic logic running through every correlator. As matches are found, they're removed from the list until we find all the matches in a big loop. And that's kind of the high-level correlation and code for that. But for resiliency, I just have some basic common things you find in a Python package. I've got some GitHub actions that will spin off and kick off some PyTest modules every time you check something in. I'm leveraging Docker and Dev containers to cover a different version of Ghidra. I have a base container I built called Ghidra Python, and basically every version of Ghidra from 10.1.5 and up is testable against the package, and it's all done within Docker. So this enables you to also not install Python, Java, or Ghidra and just try it out for yourself if you're adverse to those types of things. Dev containers, if you guys have not used those, it's a great way to create a development environment and share that in VS Code. When you git clone the repo and you open it in VS Code, it'll ask you, hey, do you want to open this in a Docker container? And that Docker container will be configured with Ghidra, with Python, with everything already set up for you. So that's kind of a nice thing to do if you're building a new package. The easy sharing of results. This is just showing you a JSON file. Not much to show you here, but just I'm capturing all the results in JSON, so you could take that and do what you would want with it. I take that JSON and I build markdown charts from it. This is an example of one of the outputs. Finally, we see some result from the tool. This is an example from one of the outputs for ghidriff posted in a GitLab snippet. This is an HTML page built from a blog post. I'm showing you the same kind of diffing. This is a GitHub gist, showing a couple of posts there, and this is a GitHub README. I'm showing you some of the results as well from diffing a kernel, and I'll walk into some more of these in detail here. And so let's talk about the features. The biggest feature, maybe sets this apart from other diffing tools, is that it's command line. Its simplicity comes from there. This is the big usage you cannot see from here. It has a lot of options because there's a lot of things going on with the tool. But basically, you just need to write ghidriff and supply the arguments of your old binary and your new binary. It does have some options for you for your Ghidra project if you want to store it in a specific location. Whether or not you want to include symbols, or if you have special symbols, you can set the path here. If not, it will go out, and if it's Microsoft, it will go out and pull the symbols from the internet. It will just do that. The engine options itself, if you can run it runs multi-threaded, so you can run multiple analysis at the same time. For debugging, sometimes you want to turn threading off, so you can do that when things become a little simpler to debug. For JVM, so you have to run a JVM. You're running Ghidra, and you're kicking that off from Python, and you might be analyzing several large binaries, and sometimes large binaries require more RAM. So you can adjust the RAM that's used by the machine, which is helpful for different types of analysis. And you have different markdown options, where you can include a side-by-side diff, change the title, or set maybe the max number of results you want. So kind of basic, but the idea is that it's command line, so it becomes a foundation for building more automation around this. Here's what a summary table of contents would look like. Kind of hard to see, I guess, where you guys are from, but it's just listing the deleted, added, and modified functions. It uses Markdown.js to build these dynamic charts. So this is just like a visual, like what was different about these two kernels. And it shows you all the modified functions, how much they're different, what functions were deleted, which functions were added. And these are things that you can just copy-paste into any Markdown-supported application. It has a binary metadata diff. So this is looking at the binary as a whole. Like it's reading off which compiler was used to build the binary, or to compile the binary, which architecture it is, and you can see the differences in the two binaries here, looking at the metadata. It includes a strings diff, where like an overall strings diff for the binary. Like here's an example of the version number changing and 2 strings being added to this. I think this is a WhatsApp binary. I can't read that from where you guys are, but it builds you the command line that was used to generate the report. So you can run the command line again. And if it's a Windows PE file, it'll actually build you the actual wget command if you want to go download the original binaries to redo the diff. It gives you the match information for each function that's been modified. So what was the match type? How similar was this to the new version? It does the meta diff or the metadata diff for each function. So what was different about the two functions? Oh, the length was different here. The called functions were different, and the address, well, that's going to be different anyway. But just it gives you more information than you usually find with other tooling. It gives you a called diff, so which functions were different between the two functions that were called. And then this, it's hard to see, but this is unified diff supported by Markdown, showing you the actual pseudocode diff that you want to see. And that's how you do your analysis, is looking at the pseudocode diff. One issue, there's more than one issue, but one issue with Markdown is it does not support styling for HTML, so I can't give you that side-by-side diff on GitHub or GitLab. You can see it in like VS Code and in a Markdown preview, but I had to build a different site, a very simple site. If you guys have seen those like, HTML preview sites, I've got something called diff preview, and if you just put in the gist ID, it will go and parse out that file that you've posted, and allow you to click on links and click on and get to a side-by-side diff view. So using this website and your gist ID, you can share a side-by-side diff view because it's leveraging HTML for that. All right, so we've got the tool. We know what some of its features are. Let's kind of look at how you can use Ghidra to do some vulnerability research or some root cause analysis. So if you just wanted to diff an entire kernel, you just grab the two versions of the kernel, run ghidriff, and it would give you quite a bit of output. Now, again, you can't see this from where you are, but I'll try to summarize kind of what it's doing. It's initializing a new project with Ghidra. It has shown you what the parameters were for the project that you just kicked off. It is going out and downloading the symbols for the kernel. It's pulling those in and applying it to the project. It is going through all the diff heuristics, and it's telling you how it matched, like each one's that matched. It's giving you the times for all of that. And eventually, it's writing out a report and a JSON file out to disk, and you can specify where that goes. That's just a really quick overview of the command line output. But in the end, it gives you something to copy-paste into a gist and share with your friends. And a nice, concise view of here are all the changes that happen for an entire kernel diff, and right there is probably about 20 lines of differences there. Now, if you're looking at CVEs, and this is kind of stems from our CVE North Stars, if we want to take a look at, this is a very popular one to diff because of the vulnerability in this one was a one-line source code change, and it looks excellent for samples. But recently, or I think this past summer, there was a Patch Tuesday, Exploit Wednesday, and that's a very common thing in our industry of where Patch Tuesday comes out, and by Wednesday we're exploiting. And I think this is Valentina and Ruben doing this, actually proving this out in one day. And they leveraged Ghidra and bindiff to find the differences between for this CVE, for this patch. And what they said was there was a missing user mode buffer check in AFD on AFD notify remove IO completion function. And so if you wanted to repeat that same diff with ghidriff, you would download both versions, the vulnerable and the patch for AFD.sys. You would run ghidriff on those two binaries that you had just done, and you would analyze the diff. If you take a look at the table of contents, you can see that function that was vulnerable printed out for you here. This AFD, it detected the change that was important. If you went and you looked at that diff for that function, you see a one-line code change here. This is a probe for write. MSDN tells me that if you go look at, it's checking to see if the user mode or the address it's pointing to is actually in user mode or not, and will blue screen if it's not. And what the diff is just showing you the change that was made for the CVE, and it's just proving out what we just proved is that we can do as good as what's out there. Here's another example. This is CVE 2023-21769. This was called, I think, titled QJumper, and this was an MSMQ. For the blog post, they listed it was in the mqsvc.exe. From the GitHub POC that I found, you could actually tell that was in this mqqm DLL, which is one of the modules within the message queuing service. And so basically, a packet parsing code in this function, CQM packet, within this DLL has the issue. So if you want to repeat that with ghidriff, you just go and download those two files, the patch version and the vulnerable version. You run this on the command line, and again, you're going to review what has been modified, what has been, and you can see right there the CQM packet function has been identified. If you go look at the diff for that, you can look at the call diff, and you can notice that, they've added some new function calls. One's called the get next section pointer safe, and they added that 7 times. I'm assuming that's what they did for the fix. This is a picture of the HTML view side by side, so not in Markdown, but in HTML. And you can see here they've added some kind of new feature check, and then a get next section pointer safe call instead of the original get next section. And so what I'm just trying to show you here is that we can leverage ghidriff to look at CVEs, just like prominent security researchers are doing. But you can also go do this for yourself. You can go, I took a CVE from August, and I didn't know anything about it. It was published last month. There was no blogs or POCs. All I knew is it said Windows System Assessment Tool. I'm like, okay, great. What is that? I went and looked on my machine, and I found something called WinSat. If you look in the description for its properties, it's a Windows System Assessment Tool. Also, it's run as admin, so maybe that's part of the privilege escalation piece. So just with that knowledge from the CV description, you can go and download that file, run ghidriff. This applies to any patching tool, and it's a good practice. But run ghidriff, get the results, and here are the results. There's not too many changes. What's been added? Another delete file via disposition. Some get file information by handle. They're adding some safer APIs, and they modified some remove all WinSat temporary files. So maybe, and if you look at the call diff, you can see they deleted, again, a delete file and a get last error, and they added some delete file via disposition. And so what I'm speculating, just by looking at the function names, and again, this is easier for Windows when you have public symbols. Like this is, I assume an arbitrary delete was the issue here for CVE 2023-36903. And then from there, you can dig in further. You could go and do your research or look at the call graph and try, how do you get to this vulnerable code path and look into it further. But the point is, you can root cause your own CVEs when you leverage patch diffing to kind of do all these things. So that was kind of I'm probably moving kind of quick, and someone should probably told me to slow down. But in summary, ghidriff, it's not a perfect tool, but it's good, and especially good when you just want to command line do something real quick and not do a lot of work to kind of get the end result. I do have some issues. I'm tracking those issues. You know, I need some more consistent code output. I'm lacking some known heuristics, and I want to add a lot more testing to kind of make this work. The unique benefits, I do think it's very simple. It's going to be open sourced. The command line is the biggest thing, and yeah, the social diffing. I think people will use this just maybe for that feature. Other diffing tools don't have kind of the easy output for markdown. I think they might after maybe they see this. But yeah, there's some new improvements coming right away. Is I'm going to add call graphs to the diff charts. So every modified function is going to receive a call graph, so you can actually see the control flow path to that binary. And I have an example of that in some of my other tooling in Ghidra comp. And I need to support global data types with Ghidra. I just need to port that over from another tool that I have. I want to add some better documentation. So in summary, we learned what bin diffing was. You learned my background and motivation for building a new tool, and you saw some of the internals and the power of CVE diffing. And so now I will open it up for any questions or anyone might have.